we'll start off with a 2D manipulator. Okay, and we'll see where we can apply these transformations, which we talked about some time back over here. So there's a hinge joint, and let's create a robot arm. Let's go to gray. And then the second link, just to make it a little bit more complex. Okay, so that's the robot arm, to distinguish it from the thin lines that we're drawing to show the different parts of the arm. Okay, so again, what we do is we will draw the fixed axis now. Okay, just like we drew earlier. So this axis is the one which we want to describe the motion about the fixed axis. And what we'll do here is we'll actually put the moving axis exactly the tip of link 1. So the way I'm drawing this is I'm ensuring that this line, the x-axis, x1, is along the link 1. And then y1 is going to be normal to link 1. Okay, so this, as I'll show you later, is going to simplify the way I derive the equations. Then I'm going to put an axis along the second link, x2, then y2. What I'm going to do is I'm going to call this point, instead of defining it O1, I'll call it P, and that's just to make my notation simple. If I call it O1, then you'll be confused when I try to write O1 with respect to frame 0 and so on. So I'm going to call that P and call this tip as Q. Okay, let me now draw the angles. Theta 1. And since x1 is along link 1, this is also theta 1. And this angle between x1 and the link shown in green is going to be theta 2. Okay, so with that, I think I'm ready to start exploring 2D manipulators. Now, this is a manipulator. You can think of your hand as a manipulator. Your shoulder is O, your elbow is P, and Q is your hand. And you want to use your hand to do useful things. So here we're trying to see how we can describe the motion of point Q, because that point Q, which is your hand, is trying to grasp objects and move objects. So what we're trying to do here is try to figure out the position of point Q. And we want to find the position of point Q with respect to the fixed frame, because most of the time we want to see how the tip moves with respect to the shoulder joint in order to do useful things. So I'm going to use some of the things we've done in the previous section to derive a formula for the position of point Q. Now, you don't need to use these formulas. You can use trigonometry here. It's actually quite simple. But what happens is when this robot becomes more and more complex, I put like 10 links. You'll see that it's much easier to use this formula which we derived than to actually do trigonometry in a 10-link pendulum. So let me do just that. Let me use the formulas to derive the position of point P. So what I'm going to do is what is known as forward kinematics. Okay, forward kinematics is find the position of the end effector. An end effector is a terminology which people in robotics use to describe the part of the manipulator which is actually going to do useful things like manipulate objects. So in this case, it's going to be point Q. So that's point Q. Given the joint angles theta 1 and theta 2. Okay, so I'm going to first start off writing the position of P in frame 0. Okay, so P is this point. And we've seen that the formula for that is R10P1. Okay, just copy paste it from the formula I wrote down for rotations. Okay, and something else I forgot here is we'll call this link, the length of the first link as L1, the length of the second link as L2. We need that. So position of P is basically given by, let's call this X, P, Y, P in frame 0 equals the rotation matrix. So cosine theta 1, because theta 1 now describes link 1 with respect to frame 0, minus sine theta 1 sine theta 1 cosine theta 1. And now comes the part where I need to write xp1 yp1. So this is essentially giving the position of P in frame 1. Okay, so what you notice is that this part is actually, so what's the position of P in frame 1? It's simply, that's the X position, that's simply L1. What's the position of P in frame, the Y position of P in frame Y1? It's just 0. Okay, so effectively when I put this down here, xp1, yp1, and try to solve for xp, I get L1 cosine theta 1 yp0 equals L1 sine theta 1. Okay, that's after doing the math. What we'll do next is try to find the position of point Q. Okay, and what I'm going to do is I'm just going to copy this figure so it's easier to do the math. Okay, so let's write the position of point Q. In frame 1, and the formula is, in this case, I know the position of point Q in frame 2, right? Because Q is described in frame 2. So here I'm going to write R21. And the reason I wrote it down this way is because point Q is between frame 2 and frame 1, not between frame 2 and 0. It's between 2 and 1. So the position can be, well, R21 is cosine theta 2 minus sine theta 2 sine theta 2 cosine theta 2 xq1 okay, and this is going to be xq2 yq2, but there's a simplification here. We want to find the position of Q in frame 2. Okay, so position of Q, or the X position of Q in frame 2, is simply going to be, this is the X axis, so it's going to be L2. position of Q in frame Y2, it's the Y position, is going to be simply 0. So if we do the math on this, we end up getting L2 cosine theta 2, L2 sine theta 2. Okay, so I just have a minute, but let me write down the formula for position of Q with respect to frame 0 and then complete it next time. Okay, so as I said, we're interested in finding the position of Q with respect to the fixed frame. So that's going to be Q0. And this is where I need to invoke the translation and rotation formula, because the way I can describe the position of Q with respect to O is through this intermediate point P. So the formula is going to be Q0 equals P0 plus R10 Q1. Okay, so P0 is something we found earlier. It's in the previous page. Q1, we just wrote it down. This is Q1. And R10 is going to be the rotation matrix of 1 with respect to frame 0, which is in terms of theta 1, which we can write. And so we can write the formula for Q0. So I'm out of time, but I'll continue from this, and then I'll show you how to animate the manipulator once we write the formula for position of point Q. Okay, so uh, that's it for today. I've posted the homework. It's not due this Sunday. It's due next week. In fact, I made it due on Monday because next Monday is a holiday. So it's going to be end of the day on Monday. Uh, if you have any questions in the meanwhile, feel free to ask me. I'm going to also send you an email on how to join Piazza, because I think that's a good way for you to contact and be in touch with your other classmates, especially if you want to work in a group of 2. Then you're more than welcome to find groups through Piazza. Okay, then I'll stop here. I'll have office hours right now. I'll be there till 12 o'clock today. If you have any questions about anything, feel free to chat with me. So I'll just review what we did last time and sort of continue from there. We talked about a 2D manipulator, which I've shown over here. There are 2 links. The links are shown as a gray line and a green line, and then they are expressed by, well, the lengths of the links, len1 and 2, and then there is the angles theta 1, theta 2. And we are interested in this problem called the forward kinematics problem, which is find the position of point P and point Q given the lengths L1, L2 and angles theta 1, theta 2. To do that, we use the rotation and translation formulas. We wrote the position of point P, this one, in base frame or fixed frame. That's the formula, and we get the position of point P. Then we found the position of point Q, which is now in frame 2, which we know in frame 2, and we can find that in frame 1 by using the same rotation formula. So here is the equation for position of point Q, but in frame 1. Okay. And finally, to find the position of point Q in frame 0 or fixed frame, we have this formula, which basically tells me that position of point Q in frame 0 is position of point P, which is the sort of the elbow joint, if this is a hand, plus the rotation matrix associated with theta 1 times Q1, which is the position of point Q in frame 1. So position of point Q in frame 1 is known. So I'll just sub these values here. P0 is, this is from the previous page, it comes out to be L1 cosine theta 1, L1 sine theta 1 plus the rotation matrix, which is cosine theta 1 minus sine theta 1 sine theta 1 cosine theta 1 times position of Q, which we've already found here. It's L1 cosine theta 2 it's L2 cosine theta 2 L2 sine theta 2. Okay, and if you expand that out, so that's x q in frame 0, y q in frame 0. If you do the multiplication and do simplification, you end up with q0 y q0 equals L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2, L1 sine theta 1 plus L2 sine theta 1 plus theta 2. There's a trig identity which I've sort of not shown here, but when you do the multiplication, you'll end up with a cosine theta, sine theta, and so on. And when you use the trig identity, which is basically the expansion of cosine theta 1 plus theta 2, you'll see that it actually works out to be that. Okay. So this is the position of point Q. And this is just telling me that I can now plot essentially given theta 1 and L1 and theta 2 and L2, I can plot or find the position of point Q. I also wrote down the formula for P, right? X P in frame 0, Y P in frame 0 is L1 cosine theta L1 sine theta 1. Okay, so given this, what I'm going to do is I'm going to draw a MATLAB program which will plot the manipulator. Okay, and this is basically builds upon what we did in the past class, which is if we are given points, then we can connect those points using lines, and all we need to do is draw lines to draw a manipulator. So I'll go through the exercise of drawing the manipulator. So next is MATLAB program to animate the manipulator. So let me shift to my other computer. Give me a sec. How I actually go about writing a code, and hopefully that will make it easier for you guys to do this. It's not really difficult to write code. You just build it step by step. So few times I will actually write the code. Most of the times I'll actually give you the code, and I will not really do the coding real time. So here's one of the times I'll do the coding in real time. Okay, so this is basically going back and forth between what I already derived and MATLAB. Okay, so new script, CLC clear all, clears all the screen components, close all, clears all the figures. And now let's do the forward kinematics. So let's save this file as, let's call it manipulator forward kinematics. Okay, so let's define parameters for the manipulator. Okay, let's say the length is 1 for both the lengths. We also need to specify theta 1 and theta 2. So let's say theta 1 is say random 0.5, okay, which is about 30 degrees, and theta 2, let's say it's about 90 degrees, so pi by 2. So next we do the origin of the world frame or fixed frame, world or fixed frame. And just as I showed in the figure, this is point O, so let me call it O equals 0, and Y O equals 0. Next, let me put the end of link 1, or if you like, call the elbow joint, and that should be in the world frame. So when you are animating anything, you're only animating your drawing positions in world frame, not any of the local frames. So xp equals L1 times cosine theta 1, yp equals L1 into sine theta 1. So this is the formula I wrote down for the position of p. End of link 2 or tip of hand in world frame is xq equals L1 times cosine theta 1 plus L2 times cosine theta 1 plus theta 2. Okay. Similarly, yq is L1 times sine of theta 1 plus L2 times sine theta 1 plus theta 2. Okay. Now since we've got the positions of the point O, P, and Q, let's now use line to connect the dots. Okay, line to generate the manipulator. So the first line goes from X, O, O. So the syntax is, if you've forgotten, help line is X comma y. So the x positions should be first, followed by the y position. So x p, x0, xo, xp, y o, y p, and say by default the lines are very thin. So I'm going to increase the width of the lines by using line width, and let me say 5, and color. Let's say that. Okay, let's run this. Okay, so apparently red is not defined. So if you want to define a string, the way you need to define a string is by hyphen. So let's see if that works. Okay, so that showed a line going from 0 all the way to 0.5. So remember, it is at an angle of 0.5 or 30 degrees. So that's what it's showing. Now, one thing which I forgot to mention in the animation class is you're not you don't need to only show colors such as red, blue, green. You can actually show any colors you want. So for example, I showed the figure in my drawing in gray, and the question is, how do you do gray? Well, all these colors are represented by, one of the methods of representing colors is by using what is known as red, green, blue values, RGB values. And if you know the RGB value for gray, then you can actually use that for gray. Okay. See this website. Okay, so here are different grays, and you can choose whichever you want. Let's say that I like the gray which looks like silver. So that's got an RGB value of 192, 192, 192. So I'll copy this. And I would paste it here. Now, the way MATLAB deals with RGB values is it doesn't take a value from 0 to 255, which is the max for R and G and B. It actually likes a value from 0 to 1. So what I need to do is I need to normalize this against 255. So it's a value from 0 to 1. Okay, so now I claim that if I do run this, I will see, instead of a red line, I'll see a gray line. Okay, there it's the gray line. Okay, so this is how you can do any color. So this will be helpful when you do the homework 1, the animation of face. If you want a different color, then you can use this trick to get a different color. Okay, so let's now draw the second line, which goes from P to Q. Okay, and that one I think I drew in green. So let me just call that either G or green. Okay, so that's how it looks. Now, one thing note is that I chose both these lines or links to be of unit length, right? 1 meter or one whatever units, but it doesn't quite look so. It's because the axes are not scaled. So the x-axis is a 0.9, y-axis is a 1.4, and that's why it doesn't quite look like a line with the same unit. So what I'm going to do is, and this is what I recommend in all animations, which is to say, you either say axis equal or you set the limits for the x and y axis. So if you say axis equal, you run this, then it looks much better because now you can see the y-axis are about 1.3 and x-axis also 1.3. You can put labels x, label x, y, label y. If you want a title, just put a title forward, kinematics, and run. And so you can see forward kinematics as a title, y, x to be the labels. And if you want to submit, let's say as an assignment, if you want to submit this, you can actually say file save as, and then you can output it as whatever you want, a PDF. So forward kinematics. So if you do that, then you can see this folder here. This folder actually generated a PDF file. So that's the drawing. So this is how you can submit the files. You could also do this thing, which is slightly less known, which is if you want to submit the code, not just the final figure, then there's a icon called publish. If you go to publish, okay, and then if you say publish, and note carefully on the left hand side, this is actually the folder. You see that there are 4 files. Now when I say publish, okay, what happened was it created the script, okay, as in a different window, a web browser. And if you look at the folders, it actually created a folder called HTML, and that's where your file would get published. So if you open that, you see there's a file called something.html. That's basically a web extension. So if you click that, you get this. But if you want to submit this for, say, the homeworks on Gradescope, it will only accept PDF and not HTML. So you could technically open the HTML and print as PDF by doing this, but there's a simpler way. So if you click on the down arrow here, and if you say edit publishing options, you can see the output file format says HTML here. You can change that to PDF, close, and now you can republish. And now if you go to, well, first of all, it generated this file. You can see it's basically has all the code I wrote down. It also produced a figure, and that file resides in this HTML folder. You can see this file, manipulator forward kinematics PDF. That's the file you'll get, and you can actually submit this file, so that way you don't have to copy stuff from MATLAB to Word and then create a PDF. You can use the publish option to do that. And we'll talk about more things you can do with publish, but for now, this is good enough for your homework 1 if you want to submit code. Okay, any questions on this? We are sort of done with forward kinematics.